Good evening, at least, well, it's 4 o'clock evening, I don't know. Good afternoon, if that's better. Once again, I'm Mr. Shale. I'm here to work through another concept of Calculus BC. In today's lesson, I'm going to work through the topics of the ratio test and the nth root test. The ratio test being one of the most frequently used convergence tests out there. Just seems to pop up a lot, particularly when you get to topics like radius of convergence or interval of convergence. So it's something you're going to see a lot. And it's also one of the more algebraically interesting tests that's out there, as well as just kind of techniques. It gets to bring lots of algebraic skills into the table. So it's one that's definitely worth playing with. The nth root test doesn't seem quite as interesting. I don't believe it's even an official AP topic, but at the same time, it belongs really nicely and pairs nicely with the ratio test. So I figure why not bring it in and just kind of address both of them so that way you get a real comprehensive view of the convergence tests that are out there. Basically today I haven't turned on the news. I've only watched a bunch of stuff, so I don't really know what's going on in the world. So rather than take a belabored introduction, I'm just going to jump right in and start to talk about these topics themselves, or at least do a quick little preview of algebraic things. So as it says here in the very beginning, some of the series today are going to feature factorials, as well as other algebraic structures and operations that we maybe don't think about simplifying with all that often. So to kick things off, I want to do kind of a quick little, I'll call it like a factorial boot camp and a ratio boot camp almost, to prepare you for some of the algebraic techniques and skills that are going to be necessary throughout using today's tools, the ratio and the root tests. So to kick things off, factorials, as it says up here, if I can find my pen, there it is. Factorials are probably one of the most, I'll say most unique elements that appear in the ratio test, that the ratio test is ready-made for. So I want to remind you about factorials because I'm not sure where any viewer might have actually seen them before or how frequently or how comfortable they are with them. So to kick things off, let's start with this. So now, if you're looking at this for the first time, you probably want to go 5, and that's obviously clever and fun, but this is actually mathematically described as 5 factorial. It has a very specific meaning. You take 5, and then you multiply by 1 less than it, times 1 less than it, times 1 less than it, all the way down to the smallest positive integer, 1. So that would be equivalent to 5 factorial, and specifically here, that would be equal to 120. 5 times 12 times 2, which is 120. So having said that, that opens up some possibilities. One interesting thing that's worth pointing out about factorials is specifically the fact that when you do 5 times 4 times 3 times 2 times 1, there's actually sort of I'll call it like a nested factorial in here. That's the same thing as 5 times 4 factorial. And you'll see why I bring that up once we start doing actual problems involving the ratio test. But for now, it's just kind of an interesting thing. Basically, it's almost recursive. Actually, it is recursive, isn't it? N factorial is equal to n times the previous factorial, n minus 1 factorial. So it's kind of an interesting thing. As far as some things that are out there worth pointing out, 0 factorial is, well, if you think about it in terms of description or counting, that's like asking how many different ways are there to arrange 0 things, or how many different ways are there to put 0 things in order. And since there's nothing there, the only order is 0, is nothing. So there's 1. So we say that 0 factorial is equal to 1. It allows everything to clean itself up. So just kind of some interesting facts up here. In fact, I'm going to rearrange this since I suddenly have a lot more space. So there's our first bit. That's our first bit with factorials, but that's not going to be the only kinds of factorials we're going to see. We're not just going to tell you to do 5 factorial. Instead, we're going to see all sorts of expressions that involve ratios of factorials. So for here, one such ratio might be this. You might be asked to simplify or work with, probably just work with, and then you'd simplify the expression n plus 2 factorial over n factorial. Now, factorial is not one of those expressions where you can just kind of go, yay, make it a big exclamation mark. It doesn't work that way. Instead, what we want to do is look at each factorial as a set of factors being multiplied, the same way we would have with 5 factorial a second ago to illustrate it. So specifically what I mean is if you wrote out n plus 2 factorial, that would be the same thing as n plus 2, and then times n plus 1, and then after that, you'd end up with n, and then times n minus 1, times n minus 2, times n minus 3. But here's the thing. The reason I paused at that spot is, of course, n times all those things is just n factorial. And once you've established that, notice that the n factorials divide out, they make a 1 for us, and we're left with just this polynomial expression. n plus 2 times n plus 1, or n squared plus 3n plus 2. So the reason I bring this up is that it gives us a nice strategy for working with factorials, especially when we have them in a ratio, which is to simply expand the bigger factorial. This is a good strategy for handling factorials in general. Sorry, it takes a while to write these things out there. The one thing I haven't been able to fix. There we go. Okay, so having said that, you might go, cool, that's not that bad, I can handle that. But the truth is there are some problems that are going to be slightly more difficult, or are going to involve a little bit more. And this one comes directly out of the work that we're going to do here. So let's say that we have this. We have 3n factorial divided by 3 times n plus 1 factorial. And again, this is something that this is something we will see, stuff very similar to this with the ratio test. So having said that, there are a couple things to do here. The first one that jumps out to my attention is I'm not going to change the numerator, but that denominator, why don't we just distribute that 3 in there? We'll write it instead as 3n plus 3 factorial. Now the reason I want to do that is if we follow that strategy from before of expanding the bigger factorial, then we just have to pick which one is larger. And clearly the one that has plus 3 is the larger of the two factorials. So our numerator up here, other than the fact that that was a miserable looking fraction bar, there we go. So our numerator up top has 3n factorial. In the denominator, we can follow that same pattern we did up here. We can start with 3n plus 3, then multiply by 1 less than it, which should be 3n plus 2. Then we can multiply by 1 less than it, which is going to be 3n plus 1. At this point, you're probably like, this is taking forever, but no, it's going to stop right there. Because then we'll have 3n factorial, and we don't need to keep going down, because once again, we have the luxury of a 3n factorial in the numerator as well. And once we've got that in place, we can rewrite our expression as 3n plus 3 times 3n plus 2 times 3n plus 1, and our numerator is just 1, because everything divided away. So the nice thing here is all of these techniques are just us working through factorials and taking advantage of the fact that factorials are full of factors that we can then divide out and make ones with really easily as we work our way through. So again, factorial is probably the newest, the most novel of the skills that will be necessary, or the algebraic things that we're going to need to play with as we dig into the ratio test today. But having said that, they aren't the only ones. So I'll call this like Recall 2.0. Here are also a couple other little mini techniques that will be really valuable for us to play with. Stuff that you just might not think about very often. And I want to say that there are really two options here that we're going to look at. So let me go ahead and just divide this page for us. Probably should have done that before, but here we are. Okay, so the first thing I want to talk about is I want to talk about exponential expressions. So first and foremost, this one throws people sometimes. There we go. Boom. So 5 to the n plus 1 over 5 to the n. So this is one that, depending on how comfortable you are with PEMDAS and different things, you may be comfortable with. But basically this is an expression where the exponent rules really jump out to me. Obviously our denominator doesn't do a whole lot, it's just 5 to some unknown power. But in our numerator we have something that has an n power, but then there's also this plus 1. Keep in mind the exponent rules say that 5 to the n plus 1 is the same thing as 5 to the n times 5 to the 1. Because of course the exponent rules say things like x to the m times x to the n is equal to x to the m plus n. However many x's are here, plus however many x's, and however many x's are there, give you a total of m plus n x's as you work your way through. Now the reason I bring that up is once we've done so, the 5 n's divide away, and interestingly enough, we end up with 5 as our expression. So with these exponential expressions, it's important to decompose. In fact, I'll even say that in there. Just like it is for dead bodies, it's important for you with exponential expressions to decompose. Could have said that for composting. There's probably other analogies to make. No, well, I think I get a button press for that. Talk about decomposition and I get an evil laugh. That's kind of creepy, but hey, whatever. It's random. Now, having said that, that's one piece. The other thing we want to look at is more of a calculus-based thing. It's something that I think a lot of people struggle with, and I will admit it took me a little while to get comfortable just kind of seeing it, but it's expressions that look like this. Nope, that's not my prettiest thing. There we go. it's going to be expressions that look like this. N plus 1 to the fourth over n to the fourth. Now the reason I bring this up is, of course, these are things we're going to see in the ratio test, but the reason I bring it up is because people sometimes have trouble seeing this. So I want to give you two possibilities that you could use that would allow you to evaluate this expression, this limit, pretty easily. So in looking here, the first one of those things I'm going to do is I'm going to point out the fact that since those two exponents in the numerator and denominator are the same, we could naturally rewrite this expression as n plus 1 over n to the fourth power. So this is one possible avenue in which to simplify this. In addition, we could then also use an exponent or a limit property, which says that we're allowed to bring that limit inside the power. So this becomes the limit as n goes to infinity of n plus 1 over n, all to the fourth. So now we're raising the limit to the fourth power instead of just that. Now having said that, the limit as n goes to infinity of n plus 1 over n can be solved and evaluated many different ways. No matter how you do it though, you get 1. So in this case, that limit's equal to 1 to the fourth power, which is equal to 1. On the other hand, there is a second way to do it. You're probably not going to like it because it involves a little bit more algebra or intimate knowledge of Pascal's triangle. But you could instead rewrite this as a literal ratio of polynomials with terms only visible. What I mean is this. N plus 1 to the fourth is n to the fourth plus 4n cubed plus 6n squared plus 4n plus 1. And I should probably check that that's true. So I'm going to quickly do one of my favorite little things. I'll write out Pascal's triangle. 1, 4, 6, 4, 1. Yep, I remembered. So anyway, that was just a way to quickly get the coefficients for that binomial expansion. But there is the numerator multiplied completely out. Our denominator is n to the fourth. And then at this point, if you so desired, you could go through and you could evaluate this like any other thing, either by using controlling term analysis or multiplying up and down by 1 over n to the fourth. The result would end up being 1 over 1, which is of course 1. So having said that, it doesn't matter to me which way you would go through. Neither one is inherently superior to the other, although obviously if you were trying to really impress the person looking at your work, you'd probably want to communicate something more along those lines. But again, you just pick your favorite way of doing it. However you see it and however you're comfortable is what's good. So basically pick your favorite method when you run into these and then attack. So having said that, we've done some algebraic work, we've done like factorial boot camp, and we've done a little bit of other simplifying kinds of things. Let's go ahead and start to take a look at at the actual purpose for all of this work, which is the ratio test. So this is the ratio test, although I also noticed that, I was going to try to separate them a little bit. It looks like they're kind of close. Honestly, whenever I see the word ratio, I always think in my head Ratio Test. Like, for whatever reason, it's always been stuck in my head. But obviously this is ratio test. It's because we're going to develop a ratio and look at it and use it as a tool of analysis to determine whether or not the series converges or diverges. So, with the ratio test, let's look at the statement and look at the three different situations that can pop up. So it says, first, in the ratio test, to let there be a series, and the terms of the series cannot be 0. So we have to have non-zero terms. Do note, though, that there's no requirement about the series terms being positive or negative or alternating or anything else. All terms go, so long as they aren't 0 anywhere. So just keep that in mind. Then the following is true. So there are three different cases that we could have in the ratio test, and it all depends on this ratio that you see if you look over here, right there. That ratio, that ratio, that ratio. So first and foremost, it says that the sum of the series, or the series, excuse me, not the sum of the series, but the series will converge absolutely. That's interesting, not just possibly conditionally or just converges, but absolutely converge if the limit of the ratio between the n plus 1 term and the nth term is less than 1. So basically we want to analyze the ratio of the next term over the previous term. Maybe that sounds wrong. The n plus 1 term over the term before it, the nth term. And we want to check the magnitude of that ratio. That's why the absolute values are there. And if it's less than 1, we're guaranteed to know that the series will converge absolutely, which means both the alternating and the fully positive versions of that series, were either one a possibility, would converge. On the other hand, the series diverges if that same ratio is larger than 1. So if our ratio is big, then unfortunately it means that our series diverges. I mean, unfortunately, I guess if you're rooting for convergence, but I don't know, be you. Finally, the last thing it says is that the ratio test fails if the limit of the ratio is equal to 1. And that's a little different. That's kind of strange, and it's going to fit a little bit even less when I talk about like the rationale behind the proof of this thing. But basically just know that we're looking to see if it's less than 1 or greater than 1. We can't do anything if it's equal to 1. But again, we will explain that when we get deeper on. Now, if you're the kind of person who has been kind of following any of the previous videos that I've posted, you know that I typically follow the statement of the test with a proof before going forward. This is not one of those situations. And the reason isn't that I don't believe the proof's important, because obviously proofs are important, and I did a lot of studying in college to be able to master some of those proofs, or even just the concept of proof, so it feels like I should include them. And trust me, I would love to include that proof. But it's pretty intense, it involves a lot of different pieces, and I feel like it takes a long time, and as I read it every time, it just kind of takes me out of the spirit of the ratio test. So unlike some of the previous ones, which I felt illuminated some really powerful things, this one I'm just going to leave the link down there. I'll probably put it in the video description as well. It's to Paul's online calculus tutorials from Lamar University. You've probably visited at some point. He's got great stuff. But if you're interested in seeing the proof, please go down there. The gist of the proof, like the biggest thing I can tell you, is that if you're looking at these, I'll call them conditions. This ratio is less than 1. Ratio is greater than 1. When you hear those words and talk about a ratio, you might think of a test you've seen before. Like, in fact, this is very similar to the geometric series test. And in fact, it's similar, not just, except for the one thing, but it's very similar to the geometric series test. And the reason for that is, if you look at the proof and dig pretty deeply, and not even pretty deeply, but a little deeply into it, you'll see that eventually it ends up boiling down into comparing with a geometric series and developing a geometric series with a ratio that's based on that a sub n plus 1 over a sub n. So again, if you're interested, feel free to take a look and see how that connection between the geometric series is really woven into this ratio test. But for my purpose, I'd rather work through the algebra of this. I think that's challenging on its own, and again, I don't feel strong enough with the proof, or strong enough that I don't have strong enough conviction that it belongs at this point to spend time on it. So take a look if you'd like to, but we're going to jump into some problems right now and start using the ratio test. Just kidding. There's one more thing I want to talk about, and that's specifically something about when you're going to want to use the ratio test. I think it's easy sometimes to get bogged down, or it's easy sometimes with these convergence tests to just get into using them in situations where you know which test to use or you're directed to use a particular test. But at the same time, it's going to be really important to be able to look at the structure of a series or the terms of a series and determine which test you want to use. So just as a quick little aside, a valuable question that you might ask yourself of when should I use the ratio test? The answer is it all depends on specific parts of the structure inside. And again, these are just general guidelines. There may be situations that break this system, but a good thing to start with is just when should I use it? The first thing that you're going to look for is if you see the presence of a factorial in your series, in the terms of your series, that's probably it. In fact, I'm going to go ahead and write always on here, but I'll keep in mind that there may be some situations with a factorial written in a very frustrating way, something like n factorial plus 42. You know, if you have that one, you don't need the ratio test, although it wouldn't hurt to use it either. But in any event, let's start there. If you see a factorial, you pretty much always are going to use this. Second, I can see what I wrote down here, but I basically want to put it this way. If you have a mix of exponential and polynomial pieces, so I think that that's really the key. I said that you could use both of them, and truthfully, like I said, the ratio test is pretty powerful and pretty frequently occurring, so you might use it more often in some situations where another test might work well. But basically, if you have a mixture of exponential and polynomial pieces, you're not going to be able to use the geometric series test. P-series might allow for the polynomial part, but not the other part. There's all sorts of other things that could pop up. So instead, I'll just put it this way. If you have a mixture of different types, including possibly a factorial, the ratio test does a really good job. It kind of lets you neutralize everything and kind of deal with everything in a really healthy, quick way. So basically, there's your quick little description of when to use the ratio test. The root test later on is also one where it's very easy to see. I'd say it's very easy to see when to use it, so just keep that in mind. Alrighty, our first example, our first problem here that we're going to work through with the ratio test, or the Ratio test. So for this one, we've got a lot of stuff going on here. You can see that the series terms are going to be kind of busy. They've got a toggle in there. They've got something exponential, and oh, there's the factorial. As soon as you see that factorial, that pretty much says you definitely want to use the ratio test. So we're thinking we're going to use the ratio test here. So having said that, let's take a look. So in order to use the ratio test, we need to take the limit as n goes to infinity of the absolute value, and you can see it's going to bug me all day, the absolute value of the n plus 1 term. So if we plug in n plus 1, we'll have n plus 2 times 3 to the n plus 1 divided by 2 quantity n plus 1. And I'll hope you'll notice how careful I'm being here as I write these expressions out. I want to make sure that everything's in the correct place and that I have parentheses around everything. I'd say that's one of the bigger issues that I see in students, is that a lot of times they just don't pay attention to parentheses. They kind of act like they're secondary, but they're really key things. So be very careful. And then in our denominator, we can put this expression down there too. So there is the ratio that we need to evaluate the limit of. And I'm just going to go ahead and say that there's a lot going on there, and that's a pretty busy expression. So naturally, one of our first things that we're going to want to do is we're going to want to rewrite this ratio in a way that's clean and accessible for us as we go to evaluate it, or evaluate its limits specifically. So there are a couple things I do want to point out here though. First and foremost, those the absolute value markers tell us that our terms are all going to be positive, and really what that does is it completely gets rid of the toggle. Basically, the toggles are irrelevant to us. We're only looking at the magnitude of this ratio. So basically what I'm going to do in the next step is I'm going to drop the absolute value lines and I'm going to drop the toggles. In a sense, it's almost like they undid one another, but it's really more like the absolute value meant that all terms became positive, so why keep carrying them around? So with them gone instead, we now have the new ratio. And I'm going to also take advantage of the fact, as I go to clean this thing up, that I can simplify some of these parts of the expression. For instance, I can write 2n plus 1 as 2n plus 2 factorial instead of that bunch of parentheses. And then my denominator, I'm dividing by that fraction in the denominator, so I can flip it and multiply. So I'm going to write this instead as 2n factorial over, it looks like, 3 to the n. So there is the limit that we're evaluating. I can put some parentheses around it just to make it clean, but that's what we're now tasked with trying to clean up so we can evaluate it and compare it to 1. Now this is just kind of a personal strategy, but once I reach this point, I tend to try to, I don't want to say group necessarily, but I want to try to rearrange, there's my word, rearrange the structure of this ratio so that all the like pieces are in the same place so that they're ready to kind of simplify and clean up. So in this case, what I'm going to do is I'm going to rewrite this as 3 to the n plus 1 over 3 to the n. And then on the other one, I'll have 2n factorial over, it looks like, 2n plus 2 factorial. So far so good? Cool. So at this point, now that I'm here, my next move has to be to clean up the ratio all the way, just to kind of complete this work that I'm doing. What that means is I need to basically decompose everything and break it up into factors that can undo one another, divide out, like clean up in multiplication, whatever the case may be. So for instance, the first one I'm going to hit is on this one. 3 to the n plus 1 over 3 to the n is 3 to the n times 3 to the 1, all divided by 3 to the n. You can see why that was a valuable move. The 3 to the n's are going to go away, but I'll be patient. On the next one, 2n plus 2 factorial is the larger factorial. And remember, my advice was that you start with the bigger factorials and start to break that one down. So 2n plus 2 factorial will be 2n plus 2 times 2n plus 1 times 2n. And aha! As soon as we hit 2n, that means that we could just keep multiplying downward, which gives us, in fact, 2n factorial. And that matches the 2n factorial in the numerator as well. So we're getting somewhere here. Having done all that, I can divide out all the factors that undo one another, and that gives me my ratio in a lot cleaner form. We now have the limit as n goes to infinity of, it looks like, just 3 by itself in the numerator, and our denominator is 2n plus 2 times 2n plus 1. So at this point, you could keep going through, but I think we're ready to actually evaluate this guy. If we plug in infinity, this gives us 3 over infinity. Actually, I'm going to put this down a little bit too, just because I want to be able to see it really well. So 3 divided by infinity, that's just 0. And now that we've gotten a number, we've evaluated the limit of the ratio. That's huge to be able to get that. We know what value the limit of the ratio is equal to. It's equal to 0. Now, as the ratio test says, we need to compare this to 1. So as we look at this, it's pretty clear that 0 is less than 1. So what that tells us is because our ratio is smaller than 1, that means in a geometric series-like way, our ratio is small enough for us to say that this converges. So in fact, we've just been given proof that this converges. But not only does it converges absolutely, which is absolutely something kind of cool and worth noting. It's not what we're asked to find, but it's nice to be able to have that consequence nonetheless. So given all that, let's go and make our final statement here. We'll say, therefore, that our series, and again, I'm going to go ahead and move this over here and put it in. Therefore, our series converges. And again, I'm a completionist, so I'm going to say it converges absolutely. It converges absolutely. And then our test, since we always have to cite the test, it converges absolutely by the ratio test. There's nothing more we have to say past that point. We didn't compare it to anything else, although maybe in the proof it does. But again, what was most important was that we showed that the series converges. And we did that using the ratio test. We took the limit of the ratio of the n plus 1th and nth terms respectively. We did its magnitude, the limit of the ratio of the magnitude of those terms. Then we simplified the expression in the limit, and we took its limit, evaluated it. We found that the value of that limit was 0. And since 0 is less than 1, that means that this series actually will converge. So we use the ratio test. The text of the ratio test says, we use the ratio test to confirm that the series actually does converge. So it would have a finite sum. We don't know what that sum is. It's definitely not 0, by the way, but we don't know what the sum is. But hey, it's still a pretty nice thing that we were able to get somewhere. Having talked about one, we might as well talk about a second one, do a second example. Normally I just do one and kind of move through this lesson pretty fast, but I've got all the time in the world since I'm just kind of doing this on my own. Talking to a computer screen. Like, computer screen doesn't make fun of me. Doesn't say anything bad about my handwriting or my drawings. So I guess in some ways the computer is a positive comrade here as I'm working through stuff. But hey, whatever. Let's look at another example of the ratio test. So this one asks us to once again determine whether the series converges or diverges. We're looking at a series that again has a lot of pieces. So when we go to start things off at this point, something that you might want to do is, of course, we know that we want to evaluate the limit as n goes to infinity of the absolute value of the ratio between the n plus 1th term and the nth. Something you can do, though, just as kind of a heads up, is since we know that the absolute value is all about just kind of making sure everything's positive, we could just kind of skip that first step and just eliminate the toggle. And so that's what I'm going to do here, just for the sake of cleanliness. And if there were people in front of me as I was giving this lesson, there'd be lots of questions of, do I have to write the limit? And the answer is yes. If you're going to write it in the way that I do, which is setting things equal to each other one step after another, you do absolutely need to include the limit. At the same time, if you wanted to just work on the limit and then come back and evaluate its limit, if you wanted to work on the ratio and then come back afterwards and evaluate the limit at the end, there is a way you can do that. But again, it's honestly, maybe it's because I appreciate everything a little bit more when stuff starts getting taken away and we get stuck in our homes. But honestly, this just doesn't feel that bad. It's honestly a really satisfying expression to write. And maybe that's why I do that little flourish with the L, is it just feels so good to do that. I mean, look at this. I don't know that I could do this all day, but I'm not disliking this process. So I don't know, maybe don't complain about the limit thing so much. And wow, did I just have an argument with myself over a hypothetical straw man complain about something that no one can complain about because I'm talking to a computer? Yeah, I did. So about that ratio, we said we're just going to ignore the toggle. We'll turn our ratio into 5 to the n plus 1 over, now let's be careful in this denominator, n plus 1 to the third times 2 to the n plus 1. And then we'll divide that whole thing. You can see how this can get a little crunchy just by nature of how much stuff's up there. We'll have 5 to the n over n cubed times 2 to the n. So as we did before, you know what, actually I'm just going to move to the next line. I feel like I'll be okay. On this one, the next thing I want to do is I want to get rid of that huge complex fraction. So I'm going to rewrite it. It'll be 5 to the n plus 1 over n plus 1 to the third times 2 to the n plus 1. And then we'll up here, we'll flip the denominator's fraction and be left with this. So as I did on the last one, once I've done that, I'm going to start to reorganize everything so that way the pieces that are the same are together. In addition, since I feel pretty confident in at least some of this algebraic work, I'm going to go ahead and decompose some of the pieces here. Specifically what I mean is I'm going to do 5 to the n as plus 1 as 5 to the n times 5 to the 1, and I'll put it all over 5 to the n. Be careful, by the way, when you're doing this step. If you're not really on top of it or you're rushing, you might lose individual factors and then end up getting the problem wrong. So just be careful here. The next one will have 2 to the n. That'll be over 2 to the n times 2. So we can see some more stuff simplifying. And then finally we have n cubed over n plus 1 cubed. So 3 things to look at. As far as things that go away, 5 to the n's divide out, the 2 to the n's divide out. We're left with, as our limit, or inside our limit, we have the limit as n goes to infinity of, it looks like we've got a 5 over 2 left over, and then we have that n cubed over n plus 1 cubed. So those two things form the limit. As far as evaluating this thing goes, 5 halves is just a scalar at this point. So I'm going to rewrite this as 5 halves of the limit as n goes to infinity of n cubed over n plus 1 cubed. And we've talked about this before. That's the same thing as n over n plus 1 cubed. And again, however you get there, like however you get to the step, I'm going to do one more step just for clarity's sake. Have the limit as n goes to infinity of n over n plus 1, all to the third power. No matter how you do it, you get 5 halves times 1 to the third, which is equal to 5 halves. Okay, now having done all that, we've got a number. We know that the limit of the ratio of those terms is equal to 5 over 2, also known as 2.5. Our next bit is to compare that to 1. So 5 over 2 is clearly larger than 1. So therefore, what that tells us is we now know that this particular series diverges. Means its terms are actually going to grow. Yes, there's that alternating thing with the toggle, but the terms are going to grow in magnitude, which means that this diverges. So we can wrap this entire puppy up. Disclaimer, please don't wrap up puppies. They need air to breathe. Don't wrap them up. Don't be Cruella de Vil. So having said all this, this series diverges. And it diverges by our new friend, the ratio test. We don't have to say anything like it diverges conditionally. No, that's not what this is about. This is just, it diverges. That's it. There's not an opposite to absolute convergence. So just, it doesn't work. Its sum grows too large for us. And so there's the ratio test. We've gotten to see an example where it converges, absolutely in fact. And we have an example where it diverges. And hopefully you've gotten a nice mix of algebraic techniques. The reason I say that is, of course, next I have a couple problems that if you'd like to try your hand at this and get a feel for it, I encourage you to take a look and kind of play with. Looking at these things, I didn't mix up anything else. Although if you do follow this QR code or the link in the video description and you try these problems, keep in mind that I ask a couple extra questions. Specifically, what I ask is, what is the limit of the ratio? And the reason I ask that is because this so strongly depends on your ability to evaluate those limits. Wanted to check that you at least algebraically found the correct value. So having said that, here are 2 problems for you to work with. Please feel free to take a look and work through them and get a little bit of practice in. I think that's probably a good idea, especially because the ratio test has some algebraic things and wrinkles that you probably don't get to use a lot. In any event, I'll take a short little break and then I'll come right back and work through the second test that we're going to look at today. So go to it. Okay, I'm back, and at this point I had said we were done with the ratio test, but there is actually one more thing I want to talk about with the ratio test, and that is just something that's kind of small that may be sitting in the back of some viewers' minds, which is what happens, or better yet, what happens, not what happens, it equals 1. Why is it that the ratio test fails if the limit of the ratio is equal to 1? And the answer is simply that there's a whole branch of functions for which the ratio test gives you 1, some of which converge and some of which diverge. So to kind of illustrate how it fails, you might even be able to anticipate it at this point. I have 2 series up here. One is the harmonic series, and this harmonic series on the left side diverges. You could say it diverges because that's what the harmonic series does, or you could say it diverges by p series. On the right, we have a p series test. In this case, p is equal to 2, which is larger than 1, which means that it converges. In this case, I'll just write p series. Here, how about I do that? I feel like I should do this. P equals 2 is greater than 1. On this side, I'll write harmonic. So there's where we are. Like we have two series. Let's construct the limit of the ratio, or let's evaluate the limit of the ratio. So in this case, we'll take the limit as n goes to infinity of it'll be 1 over n plus 1 divided by 1 over n. If we rewrite this ratio, we'll end up with the ratio n over n plus 1, and that limit is equal to 1. So at this point, it would seem like we were suggesting, based on this work, that if you get 1, the series diverges. But yeah, here's the thing. If we evaluate the limit as n goes to infinity of the n squared one, the p equals 2p series, we'll have 1 over n plus 1 squared divided by 1 over n squared. That ratio, or complex fraction, can be rewritten as n squared over n plus 1 squared. And no matter how you attack it, that limit is equal to 1. So unfortunately, what that tells us is if both a divergent series, so if we have a divergent series that gives a ratio test value of 1, and we have a convergent series that under the ratio test gives the value of 1, what that tells us is that this entire test is inconclusive in this situation. So in other words, it supports what we said in our statement of the ratio test, which is if your limit of the ratio is equal to 1, then unfortunately, the test is inconclusive, and you'll have to find another way to do the test. And obviously, in this case, we had ways. The harmonic series diverges. This is the convergent p series. We could have used other techniques to get there, but for the moment, it's just important to note that that's the reason why. Because series that converge and series that diverge, some of them at least, will give us the same value of 1, and we can't have that. That's not a conclusive answer then, so therefore that doesn't work. So in case you were someone that was thinking about why it is that the ratio test fails at 1, you now have some information to kind of help you draw that conclusion and come to understand why. With that said, that leaves us the final convergence test for us to dig ourselves into. And that is what's called the nth root test. Some places only call it the root test, so I guess I could write nth in parentheses up there. So the root test or nth root test. Basically, in this case, we're focused on a particular structure once again. So in here, it behaves just like the ratio test. The situations are if your limit is less than 1, you converge absolutely. If your limit's greater than 1, you diverge. And if you equal 1, well, as you'd probably expect, equaling 1 is inconclusive. So now something to point out here is this is the root test, and you can see in these statements that I've made here of each condition that I've used an nth root. Let me point out to you, though, that really the nth root notation that's right there, that's not necessarily going to be the only way that you'll see things. Let me remind you that that nth root is the same thing as taking that expression and raising it to the 1 over n power. The reason I want to bring this up is that oftentimes that's how I'm going to show my work. I'm not going to use the radical notation at all. I'm just going to use the rational exponent notation just because it looks clearer to me. So I want to make sure that, like in my brain, in your brain, boom, 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 in your brain you'd feel comfortable with that notation as well. So it won't always look that same way. It'll often just have the 1 over n. Now, as far as this test, like I said, the conclusion is pretty simple. Basically, what we do is we don't take a ratio of terms. We don't even have to look at the n plus 1th term. All we do is we take the nth root of the term of the general term of the series, and we check whether the limit of that general term is less than 1 or greater than 1. And in fact, I keep saying of the general term, really it's the absolute value. So once again, toggles are irrelevant in this case. We're just interested in figuring out whether or not the positive version of the terms is going to be less than 1 or greater than 1. So just like previous ones, it's worth pointing out what to look for to determine that you want to use this thing. And I'm going to make sure that I state this correctly. Basically, when I tell someone, or when I see a problem or a series that requires the root test or the nth root test, I look for any sort of stuff. It doesn't matter what that stuff is, just some sort of stuff. And then in that power, I want to see a power with an n in it. So basically, you're going to be looking for things that have variable exponents, in particular exponents that depend on the variable n. And that's going to be what clues us in to the presence or the need for the root test. So it's a very narrow subset of problems. The ratio test has a lot more flexibility. It shows up in a lot more places and cases. The root test is really specific to one structure. So, and once again, just like before, like the proof ends up being fairly similar to the ratio test proof and eventually involving geometric, a comparison with a geometric type series. So if you're interested, once again, I have the link here in the notes. You're welcome to go to that link. I'll try to include it in the video description as well. Please feel free to take a look if that feels like something that's compelling to you. But again, I'm not going to focus on the proof. I'd rather just show you how this one works. The proof just doesn't do enough for me to spend a lot of time on it. So here it is. Let's dig in and start to look at our first examples of the root test in action. So first and foremost, by giving away this is a root test problem, I've kind of spoiled part of the fun. So in here, though, if we're trying to make determinations about the root test, what I had said to look for on the previous page was stuff to the power with an n in it. And what I'd point out to you is that both our numerator and our denominator, even though they're both very differently structured, both of them have a power that has an n in it. So basically, that's the most important thing for me to note, is that there's a way of thinking about this that has the nth power inside it. So having said that, here's what I'm going to do first. I'm going to first rewrite this expression. This is just kind of my case or my way of doing it. I'm going to rewrite this series in a slightly different way. I want to make sure that nth power is on the outside, so it's really easy for us to take care of it algebraically. So what I'm going to do, and I will point out that we don't need absolute value. Well, I'm getting ahead of myself. Let's just focus on the power. This top power is already to the nth power. So there's nothing that I really have to do here if I want to rewrite it as something to the nth power. The numerator will remain n squared plus the natural log of n. So nothing too crazy there. In our denominator, though, we have pi to the 3n. So there are a couple different ways to point this out, but when you have pi to the 3n, that's the same thing as pi to the third to the n power, because the power to a power rule of exponents tells us that we multiply the exponents. So in other words, my denominator I can rewrite as just pi cubed. So having done that, now we have our series written in a way where it's very clear that everything is written to the nth power. So having said that, we can actually begin and start to look at the ratio. Or excuse me, not the ratio, of the nth root. So at this point, what we're supposed to do is we're supposed to take the limit as n goes to infinity of the nth power, or the nth root of the absolute value of all of those terms. So for our case, I've mentioned that we don't need to worry about the absolute value portion. We simply need to, since everything's already positive here, we should be good there. What I'm going to do is I'm going to write this entire thing as, let's see, should I use the radical? What the heck, I'll use the radical. So for this one, I'll use the radical. I want to talk about the nth root of this expression, which amounts to n squared plus natural log of n divided by pi to the third power, all to the nth power. Yeah. That's just an ugly parenthesis. I can do better. There we go. Now, having done that, what you might notice is we're taking the nth root of something to the nth power. What that does is it means those two operations are inverses and they undo one another. And that leaves us the limit as n goes to infinity of just n squared plus the natural log of n divided by pi to the third. Now, at this point, when we go to evaluate this limit, you might think that there's something complicated. You might even be tempted to do L'Hopital's rule. But take note of something. In the numerator, we get infinity squared plus the natural log of infinity. In the denominator, we have pi to the third power, which is pi to the third power. It's a number. It's probably something in the range of 29, 30, 31, somewhere in that ballpark. So what we end up with here, though, is just infinity over a number, which is equal to infinity. Now, in your mind probably thinks, oh shoot, we got something that's like divergent, this is really big. Well, yeah, divergence is a good thing to think of, but the important thing to note here is, as with the ratio test, the root test asks us to compare this value to 1. And one thing I know is that infinity is just way bigger than 1. So as soon as we see that piece, we know that this is going to diverge. So we've just now came to the conclusion, by taking the nth root of that series, which happened to have that n power structure, that our limit of that radical is going to be greater than 1. Therefore, we can draw our final conclusion. The series in question, which I'm going to be a lazy jerk and shrink down for us and copy without having to rewrite. Sorry for that. We now know that this series diverges, and the way we proved it was by using the nth root test. And of course you could say root test as well. I wouldn't fault you for that. I should include the word though. So there it is. And of course in your answer the necessary pieces to include are of course the word diverges and then the specific test as well. So there it is. Notice that this one worked out really nicely. It was much easier to work with algebraically than the previous one because again we wouldn't use the root test unless we had that nth power structure. And as soon as we have the nth power structure, it takes care of the whole awkwardness of having the nth root. So in other words, those things clean up and we're just basically describing what's happening with the behavior inside. And we saw in this case it definitely diverges. Our final problem that we're going to look at is one more situation that, again, right from the very beginning, as soon as you look at this problem, it really does scream for the root test. And the reason I say that is this time they're not even hiding the n. It literally has an n on the outside, raising everything inside the summation to the nth power. So basically this one is screaming root test for that reason. Like I can already see it. That little piece is saying root test, root test. It's just like it's all the way up there. So we don't even have to dig hard to get to the root of this problem. Made sure I wanted to get that one in there one more time. But we're using the root test because of that n. So let's set it up. God, asthma's terrible today. Maybe it's just dry in here. We want to go ahead and attack it like we would expect. So we'll do the limit as n goes to infinity of the nth root of a sub n. In our case, that's going to be the limit as n goes to infinity, the nth root of 5n plus 7 over 6n plus 1, all to the nth. And as we did expect, and actually, you know what, since I haven't used that notation that I almost always do, let me point out that what that's equal to is now 5n plus 7 over 6n plus 1, all to the nth power, raised to the 1 over n power. So if you weren't comfortable with the radical, there's your notation. We multiply those powers, we get n over n, which is 1, which means this is equivalent to evaluating the limit as n goes to infinity of 5n plus 7 over 6n plus 1. So having said that, that's easy to evaluate. You can use L'Hopital's rule, you can use controlling term analysis, you can multiply up and down by 1 over n. Whatever you do, you're going to get 5/6. And 5/6, codename 0.833333333333. However you do it, no matter what, it is less than 1. And as soon as we see that it's less than 1, that means that this series actually converges. So having done that work, we've now shown that the series is going to be convergent. I'm going to once again be that guy. I'm going to sneak this down here. Sneaking is probably the wrong word considering I just told you what I was doing. But here we are. We can now say, therefore, the series in question converges. And the reason we know it converges is that we used what's called the root or the nth root test. And the one thing I'll say about the nth root test is not only is it easier algebraically to work with than the ratio test, although again the ratio test is the one to know, it's the one that comes up all the time, it's official AP topic, all that good stuff. But the reason that I like the root test is it's basically all about finding a particular structure and then finding a way to take care of that structure right off the bat. We nth root everything, that eliminates that annoying piece that sticks out there and makes it a non-geometric or not a simple problem. And then from there it behaves just like geometric as far as comparing a ratio to 1. And allows us to draw our final conclusion. So there is a second full example using the nth root test. Again, I think it works pretty nicely. There are obviously some tricks. There are some twigs. No, there aren't. I have no twigs here. There are some tricks that you'll run into, but of course, like all of them have that. So it'll be up to you to kind of practice and get a feel for it on your own with whatever resources you have. Now, having said that, just like with the previous one, I do want to give you a couple problems to think about if you're someone that wants a little extra practice rather than just looking at a few examples and going from there. I think these two both, at least one of them involves a little bit of a challenge. It works a little bit harder. It takes a little bit more work to get through, but I do think they're two good problems. Otherwise, I wouldn't have written them this morning to support this lesson and give you a chance to practice what you've just listened to me describing. In any event, though, that does complete our lesson. So that is the final new topic in the world of convergence tests as far as topics that we'll include here that I'm going to make a video for. So hopefully this one has given you a good introduction and good experience with the ratio and the root tests. Hopefully it's given you some algebraic skills to bring back up and refresh a little bit as well. And more than anything, I hope that these videos have given you some insight into these topics of Calculus BC that are just huge parts of Calculus 2, Calculus 3 at different places as well. So no matter where you're watching or why you're watching, thank you for watching. I wish I wasn't stuck home making these videos. I wish I was somewhere else. But I guess that's how things go. So thank you for watching. Have a pleasant morning, afternoon, evening, or night. Goodbye now.